As we discussed in the previous slide, that increasing the pressure will increase the temperature in the condenser and the reboiler. And what it means that depending on the temperature involved, you might need a hotter utility for the reboiler, but at the same time, you can use a warmer cold utility for the condenser. Okay. And of particular interest is that increasing the pressure can help avoid the need for expensive refrigerated cooling, because now the temperature of the condenser is higher. So it means that we can use other cold utilities like cooling water instead of refrigeration systems. And these considerations lead to the design of a rule of thumb, which is that to keep the pressure low. Okay, well, only as low as the atmospheric pressure, since vacuum brings other engineering challenges as well. So it is advised to use atmospheric pressure unless the atmospheric pressure requires expensive refrigerated cooling. Okay, because if we have, for example, if we can use cooling water at atmospheric pressure, that's the best situation. But if we have to use refrigerated cooling at atmospheric pressure, then it is advised to actually increase the column pressure so that we can avoid using refrigerated cooling for condenser. The other point is that we should avoid using under vacuum. Okay, and a good reason to operate sub-atmospheric pressure is only to avoid heat-sensitive component damage. Okay. So by using vacuum, we can operate at higher temperatures without actually decomposing or damaging the components that are being separated. In general, we pay attention to the energy consumption of distillation column because they are energy intensive and because their operating costs can contribute significantly to the overall operating cost of the plant. We also look out for heat recovery opportunities, or as designers, we create heat recovery opportunities that we will see in chapter 4 and chapter 5. Remembering that the column design will affect the heat recovery in terms of both the heat duty and temperature at which the heating and cooling is required. So it is important to remember that how these design choices or these operating conditions of your distillation column can affect the operating cost of your separation technology as well. Okay. Distillation pressure is one of the important design degrees of freedom for distillation columns, but there are others as well. For example, we have the reflux ratio or the number of stages, the type of the condenser, the feed condition, and the feed stage location. Okay, so let's look at these factors one by one. So let's start with the point of reflux ratio. As you hopefully know very well, there is a trade-off in distillation between the number of stages required and the reflux ratio. And this translates into a trade-off between the capital cost of the column according to its height and the energy demand or the energy cost of the column according to the reflux ratio. And what we find in most distillation column is that the energy cost always dominate the overall costs. The energy cost may be something like 80% of the total cost. And what this drives us to do is to use a relatively low reflux ratio, but obviously not so low that we end up with a number of stages skyrocketing. The recommendation is that use 10% more than the minimum reflux ratio. Okay, so you will see higher numbers also like 1.2 or 1.5. That means 20% or 50% higher than the reflux ratio. I think these are rather old-fashioned numbers that are not relevant to current focus on sustainability and energy efficiency. So I would very much recommend for your design projects to use a reflux ratio of around 10%. That means 1.1 of your minimum reflux ratio. So next we have the type of condenser. So the type of condenser also affects the performance of the column in terms of its process economics and also its operability. We could have a condenser like a total condenser which fully condenses all the overhead vapors to form a liquid distillate and a liquid reflux, or we can have a partial condenser which forms a vapor distillate and a liquid reflux. Okay, and the choice of this condenser, like you have a partial condenser or a total condenser, depends on your operating conditions, but also your process design choices. So depending on your choice, you need a different amount of cooling, and also the temperature to which you cool would be different. In particular, if everything is fully condensed to a liquid product, then you have to cool to the bubble point temperature of the product. If you have a partial condenser, some of the material is still in vapor phase, and in this case, you have to cool below the dew point temperature, but not as far as the bubble point temperature. Okay, so again, the type of condenser dictates how much cooling is required and to what temperature. Then how we decide between a total condenser and a partial condenser? So my advice would be that if you have a low boiling material where you might need to use refrigeration, it is a good idea not to condense everything unless you absolutely have to. Okay, so then you can go for a partial condenser. But obviously, condensing everything has its own advantages because liquids are far more easy to handle. They are more easy to pump compared to vapors that you have to actually compress. Okay. Similarly, if you are handling a liquid system, your pipe size and your vessels will be much smaller compared to if you are handling vapors. So all these factors affect your choice. So if you don't have low boiling materials, a total condenser is a better choice. And if you have low boiling material, then maybe partial condenser is a better choice. The feed condition is also another important design degree of freedom. So the question is, should the feed be a vapor, a liquid, or something in between? That is, should it be subcooled or superheated? The condition of the feed affects the enthalpy of the material entering the column and clearly affect the overall energy balance of the column. And this translates into the amount of heat or cooling required in the reboiler and in the condenser. The heating or cooling of the feed affects the total heating or cooling of the system. So it is very important that we understand that what is the best feed condition. Okay. In most of the cases, we take feed as liquid because it is much easier to transport or handle liquids compared to vapors. But we definitely can have vapor feeds as well. But as I said, that just in terms of convenience, we prefer to have liquid feeds. So in your design project or in future, if you don't know what should be the feed condition, I think taking an assumption of a liquid feed should be your first choice. The last degree of freedom is the feed stage location, and we normally look at it at the end because it is affected by all other choices that we make. For example, pressure, reflux ratio versus number of stages, the type of condenser, and the feed condition. And with the feed stage location, what we try to do is to make sure that when the feed enters the column, it does not disrupt significantly what already happening in the column. That is the equilibrium at a particular stage. So normally we try to introduce the feed onto a stage where it has a similar composition and or a similar temperature. Okay, and in a binary column you can match it pretty much exactly, but in for example, if you have complex columns or multi-component columns, you can't get an exact match. But you can still find the best stage on which to place the feed by changing the feed stage and detecting how that change of feed stage location affects your reflux ratio or reboiler duty for a fixed number of stages. And a poor choice of feed location can increase your energy demand by something like 5%. So it is obviously a significant design decision. The bottom of the slide notes that not only do we have to think about the design degree of freedom for each individual column, but we also need to think about the whole sequence, because most of the time we have a distillation train in a process. So we have to not only think about an individual column, but for the whole sequence as well. So that is all for this part. Thank you for your time.